So for this problem, I'm going to draw something out here. So we'll have a frictionless surface that a box is sliding on. However, it's gonna encounter a little friction patch. So we got a box, and it's going at a nice constant velocity of 8 meters per second. Call that V1. But eventually it's going to run into this, for whatever reason, there's this patch of this frictionless surface that actually has friction on it, and it's 2 meters long. Which is going to be the displacement we're going to use for our formula. I'll use R to stand for right. So that friction patch is going to slow it down. So after it's done getting through this friction patch, now it's gotten slowed down a bit. And the new velocity is 4.0 meters per second to the right. So the question is, calculate the force of friction. So how many newtons was this friction patch applying on this box? So this is a combination of kinematics and forces. So we call this dynamics. So we have all these values about the motion of the box, but we're asked something about the forces on the box. So we have to combine motion with forces. And there's usually one link that joins those two topics, and that link is acceleration. The acceleration is found in a lot of the big five formulas for motion, and acceleration is also found in Newton's second law for forces. So that will be the link. So I'm going to use a heading here because I have multiple parts to this solution. So I want to have it organized for the reader. I'm going to start by finding the acceleration. I'm going to do that using just the kinematics. So I have V1, V2, and the displacement, and I'm looking for the acceleration. So I look at my formula sheet and try to find the big five formula that has those four variables in it. And it is the fifth one, the last one, which I will write out right now. And isolate this for acceleration. So that is going to be, so the first thing I'll do is I'll subtract the V1 squared. So I'll have V2 squared minus V1 squared. And then I also need to divide by 2 and divide by displacement. So that is the isolated formula. Plug in those values. Okay, let's see if I can do the mental math here. We got 4 squared is 16 minus 8 squared, which is 64. So 16 minus 64 is, I'm already struggling, I think 48. 48 divided by 4 is 12. And this is going to be negative. Because 4 squared minus 8 squared is negative. All right, so negative 12 meters per second squared to the right, which means it's a positive 12 acceleration to the left. Okay, so knowing that acceleration, I'm going to go and use that into Newton's second law to find the force of friction. So my free body diagram will look something like this. There's gravity. There's a normal force. They're going to be balanced out. This object is not accelerating upwards or downwards. It's only accelerating horizontally to the left due to friction. So I drew this free body diagram because I want to emphasize that I think this diagram, hopefully, maybe if you think about it for a little bit, it shows that the net force is going to be the force of friction. So gravity and normal cancel each other out. So the net force is the force that's left over, which is just friction. So I'll just write that as a little sidebar here. The net force is equal to the force of friction. And that's important to know because Newton's second law is a formula about net force. It says F net equals ma, or at least that's one version of the formula. And the net force can just be changed to the frictional force because they're the same in this situation. And it's equal to ma, so the mass is given as 12 kg. Should write that in my diagram. And the acceleration, we calculated that as negative 12. So 12 times 12 is 144. So this will be negative. This is going to go to two significant digits. So scientific notation is going to be applied here. 1.4 times 10 to the exponent of 2. Get the units in, get the direction in. So that's my answer, negative to the right, or you could have a positive answer to the left. That's your preference. All right, so that's the friction patch.